I guess we can start. So welcome everybody. It is a pleasure to have today Mariya Shcherbina, one of our members here at the Institute for Advanced Study, and she will talk about supersymmetric approach to the analysis of random band matrices.
Okay, thank you for possibility to speak here and mainly for possibility to be here during this year. It's a pleasure and honor for me. I'm going to speak about random band matrices, and here is outline of my talk. I start, of course, from main definition of the model, definition of the main properties which we are going to study, then explain why this model is so interesting for the random matrix theory, because there is some kind of crossover between localized and delocalized regime in this model, and this is the only model in the, in fact, random matrix theory. I mean, there is a difference between random operator and random matrices. Random operator, when we have something which is just near the diagonal and of order 1 near the diagonal, just for understanding. Random matrices, if we have much more random independent variables than just n near diagonal. Then I will briefly explain what does it mean supersymmetric integration. It's very simple trick and some, and it's very nice for me. And then this supersymmetric integration allows to obtain integral representation, and this integral representation would be analyzed using so-called transfer operator approach, because the expression will be very similar to partial sum of statistical mechanics, and in 1D case, then we can apply statistical mechanic approach. And then maybe it's the last few minutes. Okay, so what is a band matrices? Band matrices in 1D, here is example in 1D, is just the matrices which is, okay, you have 0 outside the diagonal, central diagonal here is square, where you have non-zero entries, you have squares. And in this place, you have this width. The width of this band is 2w plus 1, and the picture is w equal to 4. And inside this band, you have IID Gaussian entries. Mean value E, by the way, with double E is expectation through over the talk, and here expectation 0 and variance is proportional to the band width. As usually in statistical mechanics, we consider if the mean value is 0, then we consider the matrix such that the sum in the whole line and any column is 1 of variances. Here, this is the simplest case. In d-dimensional case, it is maybe not so simple to imagine the matrix. It's more simple to imagine that we have the d and we have interaction of the particle which are situated in the points of this integer points of this d. We restricted our model by some very big, like statistical mechanics cube lambda, and consider the interaction between, and this interaction depends on the distance, and again we have 0 if the distance bigger than, for example, 2w, and is IID entries when it is, when inside this so-called band again. And what is interesting, it is easy to see that even in 1D, if we put W equal to N, you obtain completely mean field matrix when you have no distance between particles, and this is a Wigner model, maybe the most famous model of a random matrix series, the first at least one. And if we take W equal to 1, then we obtain just the model with one random diagonal. And this is very simple model. And of course, for this model, it's very easy to. So there is some interpolation, but I'm going to discuss the situation when W tends to infinity together with N, and it will be some crossover when the W rate is not proportional, but proportional to N1/2. But I'll discuss this a little bit later. Here is a more general definition because, okay, we can just consider some function J, which is continuous at 0, bounded, positive, symmetric, and have piecewise continuous, and the integral in the whole space is less than infinity bounded. So the same condition, we consider the interaction mean is 0 and variance is proportional to, like it's written here, proportional to this W J of I minus J over W. And in fact, any of these, for any J, we have so-called band matrices. And I would like to consider for some technical reason, it is very convenient to consider special case of J. And here J is written like here, like the kernel of inverse Laplacian minus Laplacian W plus 1. It's just some technical reason which allow me, from the point of view of band matrices, it is some example of band matrices, but I need this special form. And okay, here is symmetric case. If we have a hermitian case, then we have symmetry in our matrices, of course. And if we have non-hermitian case, we have no symmetry. So coming back to the situation of 1D, we have completely independent entries of your matrix inside all this your matrix. So
can you explain what I think you said it that that's a discrete Laplacian, but how should I interpret exactly? That's the okay. I see.
Inverse.
Yes. Sorry.
It's an inverse matrix, and the form is like here. By the way, it's more or less clear than when you consider J rather big, then it is, or you consider some J, then you have some influence of the behavior, at least it is easy to believe, then when you have a big distance. So for Laplacian, it is important to know what's going on when I minus J tends to infinity, it becomes big. Okay, now let me give a few definitions of global, so-called global regime. Because if you have any random matrix, the first thing which you are interested in is the behavior. And if you would like to know something about the distribution of its eigenvalues, here it's lambda I, then the first characteristic, and maybe one of the most important, is so-called normalized counting measure for eigenvalues. You take some, okay, in the case of 1D, hermitian matrices, I mean, not 1D, but the spectrum, when the spectrum is real or on the, for example, on the some line like for unitary matrices, then you take delta some interval and just compute how many eigenvalues are inside this interval and normalize. Of course, you obtain some measure on the line, and this measure is pointwise and random, and also probability because of the normalization. So your problem is to study is the limit of this measure, what is the limit, and what are the fluctuations, and so on. a little bit more generally, there is generalization, so-called linear eigenvalue statistic, because some results are more convenient to formulate in terms of this linear eigenvalue statistics. Then we take some test function, any function, in fact, h, but normally piecewise continuous at least. And we take some function h, consider the sum written here. Of course, it's a random variable because lambda I are random. So this sum is random. And again, what is the limit? What is the variance? Is the CLT and so on? This question are the main in so-called global regime. And for Hermitian case, this problem was solved many years ago, at least the first one with behavior of linear eigenvalue statistic or normalized counted measure. It was proved many years ago that the limit is for measure is so-called semicircle. By the way, the same that happen when you put W equal exactly to n. So you obtain the same limit if W big, but okay, it could not be big as an n, but n, or for example, square root of n or log n, it does not matter. You even can consider the case when first n tends to infinity and then W tends. And the proof is very simple. It used methods, and also there is example for CLT. So you extract expectation and introduce some normalization. By the way, it's interesting that here normalization, if W is equal n, then like in Wigner case, you have no normalization at all. So central limit, this is a law of large number, but the central limit theorem in the endometric series without normalization at all, which is not usual for probability theory, but here it is. But now it depends on this. Again, if W and n tends to infinity, then you obtain this result. And to obtain this result in Hermitian case, we need to use some methods like moment methods or resolvent methods. In fact, both these results were obtained with resolvent methods. And all methods for Hermitian matrices are based on the simple fact that if you consider the function of some bounded interval, then the set of polynomial is dense in the set of, for example, continuous function. But if your spectrum becomes two-dimensional, then you cannot apply, just consider the polynomial. Because polynomial does not make a dense set in the, I mean polynomial of Z, does not make a dense set in the set of all continuous functions. Therefore, these methods cannot be applied in the case of non-Hermitian matrices. And here, the problem what to do was solved, in fact, many years ago. It was proposed by Yerko, so-called logarithmic potential approach based on the fact that if you know the logarithmic potential of some measure, then you can recover the measure using this Laplacian to this. And then you obtain that to know something, you need to know the Laplacian of logarithm of determinant. In fact, even without Laplacian, just average of logarithm of determinant, something like this. And here, why I will use it very often in the following. Here, why is so-called hermitization. You consider just matrix of this form. And since the matrix is Hermitian, you can use moment or resolvent approach and obtain that for any z, this y of z has okay, normalized counting measure of eigenvalues, and then it seems that the problem is solved. But the problem is not solved at all, because finally you need to do limiting transition for this measure. You know that there is weak limit, but you need to integrate with logarithm. And since logarithm is not bounded with any bounded function, if you know that there is a weak limit for the measure, it's no problem. But if function is unbounded, then you have a lot of problem, because eigenvalues could be concentrated near zero. And you need to exclude this situation. It doesn't look very serious, but in the case of the simplest model, non-Hermitian model of Geneva, it took 26 years to solve this problem. So it's a serious problem, and for Geneva it's solved, for Bent it did not solve yet. Therefore, even to prove the first result and the first one, okay, there is a conjecture that, like in the case of hermitian, when you consider the limit of linear eigenvalue statistics, then the answer is the same like for complete matrices when W equal to n. And here, of course, people expect that we will have the same like for Geneva, and for Geneva is so-called circular law. The distribution is uniform inside some disk of radius 1. So, but this is just conjecture till now, nobody knows how to prove this. Okay, now some definition for local regime. For local regime, the main object is so-called correlation function. You consider, okay, you consider the joint eigenvalue distribution P and just marginal density of this joint eigenvalue distribution. The problem is that, of course, you don't know what is a joint eigenvalue distribution. Only in some cases it is known what it is, but in fact, just formally, this is the definition. And when you consider the local regime, you need to know what's going on when your parameter, I mean, here this, for example, lambda 1 and so on, lambda k, are concentrated around one point. Therefore, this is a local regime. And here normalization n depends on the fact that, okay, you would like to study this correlation function when the distance is between eigenvalues is proportional to mean distances. Because, for example, to study gap probability, you need to know, to have interval for which probability to have it's empty is not zero. If it's zero, it's not. And then you need to study very small interval. And if you expect that the density at some point is rho, then around this density you have rho n eigenvalue, so mean distance is proportional to 1 over n rho. That is why here n. And okay, just definition GUE statistic for GUE Gaussian unitary or Wigner model. It is known that this limit exists and it's determinant of sign kernel. And for many years, it was one of the most challenging, and till now it's one of the most challenging problem of random matrix theory to prove for some models that it is, okay, there is GUE universality type for linear eigenvalue, for local eigenvalue statistic. And first it was proven, of course, for Gaussian GUE by Meta. It was, okay, 70s, many years ago. Then it was, this result was obtained for so-called matrix model, and near 2010s, 2011, because it was a number of papers, it was obtained for Wigner and many other important models of random matrix theory by the team from Erdős with different co-authors, sometimes Erdős, sometimes there are a lot of papers on this topic, but the one of the most important problem random band matrices. I will show you the results. There were a struggle about this problem, but it's still not solved. And what does it mean, Poisson statistic? Poisson statistic just means that your correlation function factorized in the limits you obtain, because if you factorized rk to the r1, then you obtain rho, and after division by rho, you obtain just you have this one. So this is definition of Poisson type statistic. Okay, for non-Hermitian case, we need to consider again correlation function defined by the same way. And here normalization is square root of n, because here we have in unit circle you have n particles. So the mean distance should be proportional to 1 over square root of n. And here the density is the same, therefore I did not put rho here. And again, here is Geneva type statistic, and here Poisson type statistic. Okay, I would just say a few words about localization and delocalization, because I use this term, but I'm not going to, in the following, I'm not going to speak about localization and delocalization, but the term is important, so I give you definition. You consider normally we study only eigenvalue distribution, but last maybe 15 years, people become to be interested what is the behavior of eigenvectors, at least in the random matrix theory. In the theory of random operator, it was much before, but in the random matrix theory, the story starts maybe 15 years ago. So we have psi eigenvectors. We normalize this by n, and we consider, we take S bigger than 2 and consider the sum written here. And of course, if we put S equal to 2, you obtain 1 because of normalization. But if S is bigger than 2, it means that in some sense your eigenvalues is, okay, they could be bigger than square root of 2, but that they are uniformly, in some sense, uniformly distributed. You cannot, for example, eigenvector which has 1 in 1, okay, 1/2 in 1 point, and exponentially decay. In this situation, you obtain here, of course, something constant if you put S, and therefore you obtain so-called localization situation. And delocalization situation is when you have, okay, all eigenvalues just simply of order 1, eigenvectors component of order 1 over square root of n. What it is written here. And also exponential localization is when eigenvectors component decay exponentially. It's written here. And why I describe this? Because in fact, I will speak about Gaussian and GUI and Geneva and Poisson statistic, but people believe that there is a link between localized and delocalized, localized and Poisson statistic and GUI and delocalized statistic. Nobody can prove it, but everybody believes that it's true, that if we have GUI statistic, you have localization, if you have delocalization, and if you have Poisson statistic, you have localization. And now, why band matrices are so challenging for random matrix theory? Because it is expected that they demonstrate so-called Anderson transition. So for D equal 1, it is expected that for W bigger than n1/2, you have delocalization and GUI. For W less than localization and Poisson. Here, for D equal to the threshold is square root of logarithm, and for d bigger than 3, the threshold is some fixed W0. In fact, I will speak today about d equal 1 mainly, and not so many results even for d. There are also some results about d equal to d and d more than 7. There is a paper of Yao Vescosa. But today I'm not going to discuss them. Now, just to show you that very serious people try to solve this problem, at least for d equal 1, just a list of the paper. Okay, here you can see that the first were Fedorov and Mirlin. They just on physical level formulate this conjecture and prove. But even for them, it's a physical level of rigorous. They formulate this conjecture that there is crossover for W proportional to n1 exponent 1/2. Then there are a lot of efforts first for W bigger than n6/7, then 4/5, then 3/4, and finally our result till now. That is why I think that supersymmetric approach is so good in this situation. We were able to prove that GUI statistic holds for W bigger than n1/2, and this is from the delocalization side, it's in some sense final theory. Okay, as for localization, then there is a result of Schenker rather old, that they did in very different way, not like we did. And okay, localization they prove from this first W much less than n1/8, then Chen Smart, it's a recent preprint, proved localization that for n less than n1/4, and there is, I would like to mention also preprint of Goldschmidt. It is stated that he proved localization for W less than square root of n, but unfortunately he died, and nobody could ask him, and people do not believe, in fact, to this result. But I think it's a problem of Chen and Smart now to show that the result of Goldstein is not true, because if it's true, then the result obtained by at the same time is not so interesting. Okay, and also I would like to mention characteristic polynomials result. I will speak mainly after this moment. I will speak about this characteristic polynomial function, and there are papers, okay, of Tatiana Shcherbina, and together with me and without me. And for characteristic polynomial, we proved crossover, and I will show you the idea of this approach, because on the characteristic polynomial, it's very easy to see the mechanism of this crossover.
Sorry, I don't understand. Was it a conjecture then, or is it really a preprint that
Sorry?
the result by Goldstein that you is it a preprint or
It's a preprint. It's a preprint.
Okay.
It's
So
a preprint, but okay, it's appeared at the same, almost at the same time when Smart and Chen.
It has proof. It has a proof in it, or just a statement?
Okay, the proof is rather complicated. The proof of Chen and Smart is the same like in Schenker paper, and it is simple, and everybody could just check it. And the proof of Goldschmidt is rather complicated, and okay, for example, I don't want to spend my time checking this argument, because for me they are not so important. I do not study localization and delocalization. I would like to know something about Poisson or Dewey statistic. And as for me, this is a problem of Chen and Smart to show that it is interesting result. Okay. Now, I would like to give you a definition because normal correlation functions are not so simple to obtain standard because you don't know what is the behavior of joint eigenvalue distribution. Normally, we don't know this. And therefore, it's more simple to give another definition of correlation function. But using this definition, we can obtain the standard spectral correlation function after some maybe additional limiting condition or something like this. And you will see below why it's so important to give this definition in this form, the ratio of determinant, because it's a form very convenient to use SUSY integration methods. And so the first, if you would like to know the first correlation function, you consider the one determinant in the numerator, one in the denominator, like here. In the case of non-Hermitian, the same, but here you need to consider this hermitization matrix Y. Here is it. If you need to know the second correlation function, then second determinant in numerator, second in the denominator. For thirds, 3 determinant in numerator, 3 in denominator, and so on. If you study the local regime, again, consider the argument which are very near to some point of the limiting spectrum. And I would like also to give, here's the definition of correlation function of characteristic polynomial. If you have only numerator without denominator, is so-called correlation function of characteristic polynomials. They are also very important for some problem of physics. I know that there are a lot of physical papers studying this characteristic polynomial, and also in some sense it's the first, at least for us, it was the first step how to study complete correlation function. I mean, when you have determinant in numerator and denominator, but it's also interesting itself. Now let me explain why it was so important to have the ratio of determinant and expectation. I would like to say a few words about Grassmann algebra and Grassmann variables. Grassmann variables, just anti-commuting variables. You have k psi variables, k psi bar variables, all of them are anti-commuting. Bar does not mean that there is conjugation or something like this, just independent set of the same number of anti-commuting variables, just tradition to put bar. Now, what we have, if we have anti-commuting, of course, we have that square is equal to 0 for each psi and also psi bar. If you have any linear combination, of course, you have also 0. And now our problem to define algebra on this Grassmann variables, and we consider the analytic function. I mean that the function can be expanded in the series. And we consider the analytic function, and instead of 2k variables, and instead of 2k variables, put here in this expansion, I mean in the Taylor series, we just put these Grassmann variables. Of course, the sum will be terminate after some point because of this property. Because you can have only the biggest exponent of psi, the number of psi is k, and also k psi bar, so the series will terminate, so you have polynomials. And to have algebra, you need also, okay, you need to say something about the order of this, because if you exchange the places, then the sign will change. So you need to set what is the correct order. And on this set of function, you define some linear function. I can say from the very beginning what does it mean, but it's more convenient to give the definition like it's done, for example, in the recent books by induction. So we write that deep psi integral from deep psi is 0, and psi deep psi is 1, and the same for psi bar. And then we agree that multiple integral is repeated integral, and the differential sign are also anti-commute. So there is some fixed order written here. And now, if you have function on your algebra, it's more or less clear that contribute, and you come, this is polynomial, and you apply your functional to this polynomial, and you obtain something non-zero only for the term which contain all psi and all psi bar, because of this property of this. So it's just a coefficient in front of the term which contain all this, I think. Okay, definition is definition, but important feature of this definition is that if you define in this way the integral, of the quadratic form, then you obtain determinant. And it's very similar like in the Gaussian case, when you have some function which is positive, you obtain inverse determinant like this way. So combining this formula, I can obtain the ratio of determinant, integral representation of ratio of determinant. Now, if I do like this, yeah, I obtain something like written here. I need to introduce two families of n Grassmann variables, then I can write my determinant, the correlation function of determinant like here. And then what is important then, okay, here you have some exponent, and its exponent is linear with respect to h. And h contains random variables, Gaussian random variables. So you can average, because the exponent, to average exponent, linear exponent of Gaussian variables, it's very simple. One can do this without any problem. The same, in fact, in the case of non-Hermitian situation, but here you need to take, in fact, you need to put here y, but it's more convenient to give some linearization of the matrix y. This matrix has the same determinant, but it is linear with respect to h again. And so you obtain again some linear representation, which you can average with respect to your randomness. And after averaging with respect to your randomness, and then you obtain some, of course, you obtain some expression, some integral with respect to psi, your Grassmann variables. But the expression is of the kind that, in fact, after some trick, you can obtain, you can take this integral. And after taking this integral, why I like so much, you obtain the situation when you have partial, in fact, you have partials, typical partial sum for some d-dimensional statistical mechanics model, because representation could be obtained for any d, the same will be for any d. So you obtain partition function for some statistical mechanics model with nearest neighbor interaction. That is why we took this Laplacian, because here it's yes, neighbor interaction because of Laplacian in the function j. You remember, I introduced my model with the function j, which is inverse to Laplacian. And after averaging, you obtain in the place of inverse, you obtain matrix and self, and here you obtain Laplacian. And the same, so here you obtain this model with respect to here potential, which is of course non-real. And this is one of the main problems. The potential is non-real because here the matrices X are Hermitian, but potential is real and is not real. And in the case of non-Hermitian situation, you obtain almost the same, a little bit different potential, but the matrices are not real. They are arbitrary 2 by 2 matrices. And okay, I would like to say that in fact, the first two expressions were written for the function of correlation, a correlation function for characteristic polynomial, but for the first and the second correlation, real correlation function, you can write representation in the same form. And what is important then, it is written in the form like here, which is in the case 1D, it is, in some sense, it is a product of the operators. So it's very simple observation. Then if you have expression like before, then you always have that it is, you can introduce the integral operator with the kernel k of x1 and x2. And then if this operator is k, then you obtain that what is written here, this partition function becomes the n-1 degree of this operator. And so if you know the spectrum of this operator, then you know how does it look, the sum. So if you know the behavior of eigenvalues, then you know all about it. You need not to study this sum, you need just know what are the eigenvalues of this operator. Okay, but there is a rather essential difficulties that first of all, your operator is not self-adjoint. And the self-adjoint operator, and I'm going to study the situation when you have operator and some perturbation of this operator, which will depend on your small perturbation of parameter. And when you have self-adjoint operator, then it's very well known how to do, what will be the perturbation and so on. If you have non-self-adjoint operator, you have a lot of problems. Every specialist in the operator theory will say you the same. So, in fact, it's much more convenient to study the resolvent methods. When you write, you consider G, which is the resolvent of your operator, and you write our partition function because Kn f G n-1, but n-1 or n is not so important. So n, forget about -1. So you have n degree of operator, so you need, can write this like this integral. And so if you know the resolvent, you know all. And with the resolvent, the situation is more simple. You need to know also, okay, again, you need to analyze this resolvent, but it's more or less clear that if resolvent is bounded, reasonably bounded, then, for example, if z is modulo z is smaller than 1 minus log square, then the contribution will be 0, final contribution. So it's convenient to introduce the definition of asymptotical equivalence between operator, and here is the definition. The definition is you choose some special contour, in any case, in some special contour, And here you prove that your operator in some sense are equivalent in this contour. And if you are able to prove, because, okay, the complete partition function is the sum of this contour with the sum, the integral with respect to the contour on what I am calling L2, which is a small z. But this does not contribute, so you have that the resolvent gives you the same. And now, okay, now the main technical step here is that we have some operator k, but we would like to see it, how does it look if we change the variables. We change the variables from the matrix X to this unitary transformation. Here is diagonal, and we obtain that your kernel looks almost like a product of the kernels. It is not exactly the product because this T, which is here is an operator with respect to unitary matrix, here operator with respect to numbers, positive real numbers, and here also real numbers. And these two operators looks like standard operator in statistical mechanics. And here you have the problem that this T dependent on A and B. So there is no tensor product from the very beginning, but you know that the dependence only through this T. And the key step is to prove that it is not important that there is this T, because we have a limit when term W and n tends to infinity, we have a limit for this T, and you can substitute by limiting T and analyze just the product, tensor product of two operators. And here A, it's something like this, and U is, something like this with T equal to 2 tilde, 2 stars, sorry. Why it's so convenient? Because when you would like to study what is the dependence on your perturbation, constant which does not depend on perturbation are not important for you. So it's very natural to introduce some constant which, to divide your expression, the second correlation function by some constant. And this constant is just correlation function without perturbation. And if you define, then you obtain that if you have the, equality before, then you need to know, in fact, only the spectral property of K star. And with K star, there is a good news because K star is self-adjoint. And moreover, it is a so-called difference operator. And difference, it means it depends on the kernel depends on the U1, U2 star, like it's written here. And it is known that all operators with the kernel like this compute with a shift on the unitary group. And therefore, it is known what are the random eigenvalues and not non-random eigenvectors and eigenvalues. Because you know that in this situation, your operator will be constant on each reducible representation. So you just consider the eigenvectors in this reducible representation, they are Legendre polynomial, and then you obtain results. And now, what is the mechanism of crossover for W minus 2? Here the main point that eigenvalues are like this. Like this. So you have this. And if, so the spectral gap here is proportional, all gaps is proportional to 1 over W square. And if N and your perturbation is proportional to 1 over N. Now you compare your perturbation and spectral gap. If the spectral gap is much bigger than the perturbation, then you obtain that all eigenvalues except the first one, and the first one for difference operator is always 1, tends to 0, and only the first one tends to 1. So you obtain just projection. And in the case of this projection, you can compute what is the limit, and you obtain 1 like in Poisson statistic. And if W is much smaller, W minus 2 much smaller than perturbation, you can write the nth degree of your operator like it's shown here. And it's easy to see that, okay, here, this term does not contribute because you have this equation. So you obtain that, and perturbation term is just multiplication operator. And so you obtain as a limit, you obtain just this multiplication operator without normalization. And if you have W square proportional to N, then you have that the N degree of your K star operator is proportional to this. And you obtain that your operator in some sense is the sum of Laplacian on the unitary group written here plus multiplication operator. And after this taking nth degree, you obtain the answer that there is intermediate regime. In fact, it's the only example where it's something is known about the intermediate regime. And now, as I told in the beginning, I have a few minutes to present the result, which in fact I described before. And here's the result about, first, about Hermitian case. In the Hermitian case, we have that the limit, there is, okay, GOE statistic in the case of N less than W square or W bigger than N square, then for much bigger we have Poisson statistic, and when proportional we have this special kind statistic, some intermediate statistic. And we start to do the same for non-Hermitian case, and the first theorem which we already obtained when I'm here is the result that, okay, when we are in the localization field, then we obtain Poisson statistic. Okay, thank you.
Questions?
Maybe can you remind us what it like this? Maybe a stupid question. What is 1D? What is a 1D matrix? What is a 1D random band matrix? Like this is you have some dynamics on the line.
No. Okay, you consider the matrix in the simplest situation.
It's 2 by 2 matrix.
No, it's n times n matrix. N times n matrix, very big matrix, and you can see there's a band inside, which contain outside the band you have 0, and inside the band you have something which is okay, IID up to the symmetry or without symmetry condition, and mean 0, and the sum of the variance in each line is 1. And then you have this matrix, and you consider the regime when n and W both tends to infinity.
What is my question is, what is one dimensional about this?
One dimensional means that, okay, your matrix, because it's easy to draw what is your matrix in 1D situation when it's, okay, just n side n. And now try to imagine the matrix of interaction of the system situated on the ZD. You have ZD and you have interaction, and your matrix is a matrix of interaction. And this interaction depends on the distance between particles. And if the distance is big, then no interaction. And if the distance is less than 2W plus 1, then you have something zero mean again, and so on. So it's not so simple to draw, of course, matrix, to draw matrix.
It's always about
It depends on the way how you because you have not natural order, how to enumerate the points. It's easy to enumerate with a D parameter, but with one, if you would like to have matrix, not so simple. Just try to imagine that it is a matrix of interaction. But after using, for example, nobody have doubt what does it mean d-dimensional discrete potential. In some sense, it's the same. Oh, discrete Laplacian. Sorry. Discrete Laplacian in one-dimensional, it's just Jacobi matrix, but in d-dimensional, it's difficult to say what exactly does it mean. But it means that you have some interaction between sides with the distance, for example, for Laplacian 2. Exactly 2. That is why I did not try to draw a d-dimensional case. But physicists consider Anderson model is formulated because the model came from statistical mechanics. In statistical mechanics, everybody understands what does it mean d-dimensional d-dimensional partition sum. But if you have d-dimensional partition sum, you can speak about matrix of interaction.
So it's the matrix of interaction for a 1D model where the particles are only interacting.
You just have you have some particles on Z, so you can enumerate 1 and so on to n, and then you have interaction between them when the distance. And when you have d-dimensional, just do not try to imagine. Just it's formal definition, but normally after some, for example, here after some manipulation, I obtain the expression which, just like partition sum for statistical mechanics, in which is interaction of nearest neighbors. And it is very easy to understand what does it mean. And you need to work with this sum.
But I also wanted to ask, like you also said, you made a distinction between random matrix and random operator, and I want to understand what that distinction is.
Okay, the difference is just in some sense formal. Normally, it means you say about the random operator when the number of a random parameter is in some sense proportional to n. For example, if you have Jacobi matrix with random diagonal, it's operator. Another way to define, to say what does it mean operator, when you have operator, you can say what is the limiting operator. Because, for example, if you consider Jacobi matrix with a random diagonal ID, then you can say that, okay, at the end you obtain two-dimensional, you have this difference operator with a random potential, so there is limiting object. When we speak about random matrices, normally we have no limiting object because, for example, just imagine what's going on if you have Wigner model. Wigner model means that you have, in each side you have something of order 1 over square root of n. When n tends to infinity, you obtain 0. But if you try to compute what's the distribution of eigenvalues, this is not zero. And also local distribution is also not zero. So it's interesting object, but you cannot define the limiting object. And normally it's happens when the number of independent random variables much bigger than n. So for W, you have random band matrix is W is okay, big. When it's fixed, it's operator. When tends to infinity, then it's matrix.
Is there a way to understand the reason why in 3D you expect the delocalization so fast? It's
Okay.
related to transients of random walk or?
In some sense, as far as I know, yes, but I'm no specialist. I need to try to understand. For me, it's okay. This is some physical reason, like an Anderson model, by the way. In Anderson model, everybody believes that, okay, in 1D you have complete localization, in 2D you have some threshold, and starting from 3 you have complete delocalization. And there are some physical arguments behind this, but okay, if you believe that in the situation of Anderson, you have just delocalized vector, but in Anderson you have only one random diagonal. Here you have a lot of random diagonal, so you can believe that if you add another randomness, you will still have delocalized situation. Just like this.
And if you are or something that is mixes much faster, like an expander, if you replace the box in Z2 or Z3 by an expander graph, is it known that there you have very fast delocalization?
No. Okay, at least I don't. But in fact, so many problems with 1D for band matrices. You see the effort, and till now, for example, nobody able to prove Poisson statistic. Because we can write representation and use operator method, but just to understand, this transfer operator is now not just a kernel, but it is a matrix kernel. And matrix kernel is, okay, just imagine 70 times 70 matrix kernel. We need to choose, in some sense, main block to introduce some transformation and so on. So the paper about GUI statistic when W is much bigger than square root of n, it's not a simple paper. It's rather hard analysis. And also, okay, the idea, of course, is to use saddle point methods because you have some big parameter in the exponent. And it's typical when you have big parameter in the exponent that you immediately, if you are analyst, at least it comes to you immediately to use steepest descent methods. But even if you are able to prove steepest descent, what does it mean? You find this saddle point and expand around the saddle point. But if your function depends, for example, even not 70, but 20 variables, and you need to study not the first term of your expansion, and for example, 8th term of your expansion, you can imagine how many derivatives you can compute, and you need to prove that in this expansion all integral disappear, and some of them are simple, some of them are not so simple, so it's hard analytical problem. And with the localization phase for us, it was a problem that here I describe when you consider only correlation function of a characteristic polynomial, your operator is always compact. So you have only discrete spectrum. But in situation when you have both numerator and denominator, I mean ratio of determinant, then you obtain some additional operator which is, okay, has continuous spectrum. And the argument with spectral gap does not work anymore, but in situation when you need to prove delocalization, you just need to prove that operator tends to 1 in some sense. And tends to 1 you can do even for the situation when the spectrum is continuous. But if you are in the situation of delocalization, you need to prove that your operator tends to some projector operator. And when operator can have continuous spectrum without gaps, without any spectral gaps in this situation. So it's much more complicated problem. And then, okay, in fact, for us it was, we tried, but after some time of efforts, we decided to leave this problem. Maybe we need some fresh idea, I don't know, but to write a spectral supersymmetric approach is very good in the sense that, okay, you obtain immediately the partition function of some statistical mechanics model with a big parameter, and you can use transfer operator approach. But spectral analysis, yes, it is not so simple.
Okay, if there are no other questions, let us thank Mariya again. Thank you.